Good morning, good afternoon, good evening. Welcome to our Chapter 8 lecture. Today I want to start Part A of Chapter 8, Chemical Bonding. And if time allows, I will also start Part B. Chapter 8 is on basic concepts of chemical bonding. First, before we look at the section for each part, we should be able to define a chemical bond. What is a chemical bond? A chemical bond is simply a strong electrostatic force of attraction between two atoms, what hold atoms together. And there are three types of bonds we will cover in Chapter 8. I know for those who took into chemistry, you are aware of the three types. The first one, ionic bond, covalent bond, and metallic bond. We will see each one of them as we go along with our lecture. As usual, the chapter is broken into two parts. There is part one in part two or part A, part B. Part A covers section 8.1 through 8.4 and 8.5 to 8.8 part B. 8.1 we look at the Lewis symbol for element and the octet rule. We look at ionic bonding, covalent bonding, bond polarity and electronegativity. Part P, we look at how to draw the Lewis structure for molecules and polyatomic ions or just ions. And we move on to the resonance structures, that is structures of the same molecules having either double bond or triple bond in different location of the molecule. The exception of octet rule, there are some three basic exception of octet rule in drawing Lewis's structure. And lastly, we look at the strength and length of covalent bond. By then, you should be able to define or differentiate the three types of bonds, okay, ionic bond, covalent bond, and metallic bond. Now, chemical bonds, there are three types, as I explained. There is ionic bond, which is electrostatic force between ions. Remember, when we say ion, here it could be cation, all right, which are positively charged, anion, negatively charged, or polyatomic ions, which we looked at earlier on. So strong electrostatic force of attraction between these ions, or what is holding the ions together is ionic bond. Usually we have either metal plus non-metal or metal plus polyatomic atomic ion. So if I see a compound made up of a metal and a non-metal, I know that that has a ionic bond. This is an example of ionic bond where there is the blue spheres with positive represent sodium cation, and the green spheres with negative charge represent chloride ion, okay, chloride ion with a negative charge, Covalent bond, these are bonds between two non-metals, all right? Covalent bond, simply this is bond between two or more, or just say non metals. You know where the metals are on the periodic table, non-metals. This one, they involve sharing of valence electrons, sharing of valence electron to fulfill the octet rule, which we will look at later on. So here, the sharing of valence electron in the outermost shell, when atoms, non-metal atoms, do share their valence electrons to fulfill the octet rule. An example here on the diagram is this water molecule you see here, right? Water molecule is made up of hydrogen, the white sphere, and oxygen. The type of bond you see here is the covalent bond. And lastly, metallic bond. These are the bond which holds nuclei in metals. In this one, in this type of chemical bond, the nuclei of atoms just float in a sea of electrons. It's what hold metals together. An example here is either it could be a metal such as iron, a metal such as sodium, right? So here in metallic bond, atoms are held together. Maybe if I blow up this, you'll see that the metals or the nuclei of metals are floating in sea of electrons, now let's see 8.1 Lewis structure. First of all, let's understand what is Lewis before we look at the octet rule. Green and Lewis was an American chemist who proposed that when elements on the periodic table react, they make use of their valence electrons in the outermost shell. And those valence electrons are, he proposed or devised a method of showing those valence electrons by using the chemical symbol and the dot representing the valence electron. This method denotes electron by using the dot here for every valence electron. Let's understand what valence here. Valence electrons are electrons in the outermost shell, okay? Valence electrons, these are electrons. What electrons in the outermost shell, or electrons in the highest n value. So if you write the electron configuration for, when you write the electron configuration for any elements, the total number of electrons in the highest n value gives you the valence electron for that element. For example, chlorine, which is number 17, let's see how you determine the valence electron. Electron configuration is 1s2, 2s2, 2p6. This gives us 10 electrons, 3s2, 12, and then 3p5. Most students confuse the outermost subshell here and say it's the shell. No, you have to look at the highest n value. The highest n value here is 3s and 3p, or the highest N value is 3. So valence electron is 2 plus what? 2 plus 5 equals to 7. But when you look at you don't have to write the electron configuration for elements to identify the valence electron. Valence electrons, all right, here, valence electron given the periodic table. By now, you know the vertical column for representative. Representative elements are those groups with a number and letter A. A number and a letter A represent the main group element or representative. And it turns out that group number represent the valence electron except helium. Helium is in group A, all right? And it has only 2 valence electrons. The rest of group A, they have 8 valence electrons. So what this means is group number 1, they have 1 valence electron. Group 2, 2 valence electron. 3A, 3 valence electron, and you'll only see the common one. So given the periodic table, you should be able to identify or state the number of valence electron. And now the Lewis dot symbol for element is simply the chemical symbol for an element, such as, for example, let me title this Lewis dot symbol elements. So if given any element on the periodic table and you are asked to draw the Lewis dot symbol for that, it's simply the chemical symbol and the dot representing the valence electron. Calcium is in group 2, so I'm just going to represent that using the 2 dots. One thing you need to remember is you don't pair until they are singly distributed around it. Lithium is in group 1, so I'll have 1 dot. Magnesium is in group 2, so it's just going to have 2 dots. Aluminum is in group 3, so it's going to have 1, 2, 3. It has 3 valence electrons. What is for group 4A, 1, 2, 3, 4. They are singly distributed around. You can do the clockwise or anti-clockwise. Now, beyond 4, let's say nitrogen. Nitrogen is in 5A, so 1, 2, 3, 4, 5. And if I look at nitrogen, it has 2 paired electrons. Oxygen is in group 6A, so 1, 2, 3, 4, 5, 6. This is the dot symbol for oxygen. For all group 8, all right, or rather before we get to 8, all group 7, such as fluorine, 1, 2, 3, 4, 5, 6, 7. So that's how you write the dot symbol for all group 7A, except for helium in group 8, all group 8 element will have 8 paired electrons representing the valence electron. Now, this valence electron here, elements can either lose or gain valence electrons, say that they end up with 8 electrons in the outermost shell, which means they end up with 8, hence this octet rule. To achieve octet rule, an element can either gain, lose, or share electron. And remember, electrons are negatively charged. This will impact how we look at the gaining and losing or sharing. Metals tend to lose. So anything on the metal part on the periodic table, you know where they are, the metals tend to lose their valence electrons. For example, sodium will lose 1 valence electrons to form Na positive plus an electron. We know will lose one valence electron. Non-metals tend to gain, all right? Or they share in order to end up with 8 valence electron. We call these what? We call these octet rule until they end up with 8 valence electrons to achieve the octet rule. Here is a learning check all right. Are all these Lewis symbols for chlorine correct? And remember what we went through on writing the dot symbol for Lewis dot symbol for an element. It's just a chemical symbol, and the dots around the chemical symbol representing the group number for main group. So in this case, if I look at the first two, the lone electron here and paired, it can either be on the left side, it can be below. But if you count the dots around the last structure here, this has 1, 2, 3, 4, 5. It has 5 less, so this is wrong. This is wrong. No, the first two are Lewis structures because of the different placement of unpaired electrons. Yes. So this one is correct. This one is correct. No. All right. The correct answer is B. The point here is you should be able to draw the dot symbol for or any element. In this case, for main group, you don't need to memorize. You'll be given the periodic table. You'll be given the periodic table. Let's see. Typical question in the quiz. There are dash and paired. No, there are dash paired and dash unpaired electron in Lewis symbol for fluorine. We just did that. All you have to do is draw the dot symbol for fluorine. 1, 2, 3, 4, 5, 6, 7. So there are 6 paired electrons. All right. There are 6 paired electrons. This is what I was drawing, going around. 6 paired and 1 unpaired electron using the negative charge. The correct answer is C for this, so you should be able to see that we say these are paired. All right, this is a pair, this is a pair, this is a pair. So here they are paired. And here is an paired. It's not paired. Unpaired electron. So correct answer is C for that. Let's go back, dive into ionic bond. I explained earlier on when I was giving you examples of chemical bonds. Ionic bond consists or is made up of 2 things. Metal plus non-metal, or metal plus polyatomic ion. So if I see a chemical compound, or just a compound with polyatomic ion and a metal, I know the type of bonding in there is ionic bond. It involves transfer of electron from what to what. Remember, metals tend to lose electron. Non-metal gain electron to achieve group 8 valence electron configuration. So there is a transfer of electrons from metal to a non-metal. You see a metal plus non-metal, in this case, the formation of sodium chloride. There is transfer of what? There is transfer of electron from sodium to chlorine to form chloride. This process is highly exothermic. Remember, electron affinity is the energy given off when you add an electron to an atom. So this will form a cation, which is positively charged, and the chloride, which is negatively charged. And we know positive, negative to attract, positive, positive repel, negative, negative repel. This type of bonding exists between nonmetals on the left side, except for group 8A, of course, they don't react because they have their outermost shell fully complete. Here is an example of using sodium chloride. Okay, there is a sodium, there is a chlorine. Mixing the two is highly exothermic in the formation of sodium chloride. Sodium chloride. So there is one element losing, the other element is gaining. Recall the ionization energy. Metals tend to give up or lose their what? Their valence electron. They have low ionization energy. Remember, ionization energy is the energy required to remove an electron from an atom in its gaseous state. Metals, they have low ionization energy. Non-metals, they have high electron affinity. Therefore, the arrow indicates the direction where the electrons are moving to, from sodium to chlorine in this case, and we indicate extra electron using an overall charge of negative. No one will ask you to draw this, but you have to know or be able to recognize the type of bond given a chemical formula for a compound. I may not know, all right, the chemical name for a compound such as this, all right, I may not know the name, for example, but with the periodic table, identifying the location on the periodic table of each element, this is a metal and a non-metal, then you should know that it is ionic bond based on the location of each element. So ionic bonding is not only restricted to sodium chloride. If I can see that there is a metal and a non-metal, or metal and a polyatomic ion, then you should be able to conclude that it is ionic bond. For example, iron 3 hydroxide, this is a polyatomic ion involved in there, hydroxide. Right, if there is a carbonate, then you know that is what it is. Now, properties of ionic substances, they are brittle, and by the way, you need to know all these properties, covalent bond compounds and ionic substances. They are highly brittle. What that means is, you know, if you take a hammer and you strike, they will just shatter, because if you align, if we use a hammer and align green and green together here, they will tend to repel, therefore leading to high brittleness. They have high melting point, all right? They are crystalline in nature because of the crystal structure. They are crystalline because of regular arrangement, repeating pattern of negative, positive, negative, positive. They can easily, they cleave well, that means they form nice, round, smooth edges, lines at the end when striped. Now, formation of ionic compound is highly exothermic. They give away heat. Energy is released, all right? And the energy required for this we call lattice energy. The energy required to completely separate 1 mole of solid in ionic compound into its gaseous ion. Be able to define that. That's the total energy. It could be in kilojoules or joules required to separate 1 mole of solid ionic compound into its gaseous ion. For sodium chloride, separating sodium from chlorine in solid form gaseous sodium ion and chloride ion in gaseous state, the minimum energy. And look at the units per mole, which means we need 1 mole of NaCl. It is positive 788 kilojoules per mole. And understand what this means. It's endothermic. That means we need energy to separate the 2 ions. And the amount of energy required to do that is called the lattice energy. Here is just few compounds, few ionic compounds with their lattice energy. If you look at the trend here, don't just look at the numbers, and even though you will be given the periodic table, there is a trend here with respect to the ionic size. Lithium and fluorine, lithium is smaller than cesium, and if you look at these, the 2 nuclei are close, so it's hard to break apart. Therefore, high lattice energy as you go down. The size on the charge also affect the lattice energy. Born-Haber circle, this is used to determine the lattice energy of a compound. I won't go in details into calculation of the lattice energy, but it just works, or it's the same way as you calculate the Hess's law, using Hess's law to calculate the enthalpy for reaction, enthalpy for reaction. The most important thing here I want you to take moving forward is the trend on lattice energy. If you look at the first diagram with the blue here, lithium, sodium, potassium, rubidium, cesium, the ionic radius keeps on increasing, whereas the lattice energy decrease. Reason for that is if I have let's say this is lithium and potassium, for example, and rubidium, if you look at it, the size is getting larger and larger. If chlorine here or fluorine is constant throughout, the distance between the 2 nuclei keeps on increasing as you go down. So just think of it as you have a small stick. It's so hard to break, but if you have like a longer stick, it will be easier to break apart. Hence this trend that as the cation radius increase, the lattice energy also decrease. As the anion also increase, the lattice energy decrease. It just follows the same trend. That is the trend I want you to remember, because you will be given a series of compounds and you are asked to either rank them according to increase in lattice energy, or state which one has the highest lattice energy and so forth, only with the periodic table. For example, here in the next slide, in this slide right here, please place the following in order of decreasing magnitude of lattice energy. We have sodium fluoride, rubidium bromide, and potassium chloride. You can use elimination method. Rubidium, in the cations, if I look at the rubidium, has the largest, all right, has the largest, and what we want, decreasing, that means should have the greatest. This should be the least, and if I use elimination method, A is wrong and D is wrong. Now we are left with B or C. The reason why A and D are wrong is we should have rubidium bromide as the last because of the size of what? The cation. So if I look at two cations here, chlorine is larger than bromine, so it should be the other way around. Potassium bromide, chloride, should have less energy. So in other words, sodium fluoride should have greater energy than potassium chloride. And the correct answer is B, sodium fluoride is greater than potassium chloride, which is greater than rubidium bromide. So here, using the periodic table without having the numerical values, as you go across, all right, atomic radius. This is a trend we looked earlier on. This decrease, decrease, and then coming down. This means increase, increase, decrease. As you put, it will help you in making a conclusion. It's just based on what we talk or we look at here. And trend on atomic radius, ionic radius, we look at it earlier on in chapter 7, periodic trend. Periodic trend, correct answer is B. Let's go back to electron configuration, and in particular, electron configuration of ions. Main group, main group, these are the elements on the periodic table, the first two and the last six on the periodic table make up what we call main group. And metals tend to lose their valence electron, resulting in configuration of the previous noble cast. For example, sodium will lose its one valence electron, Na++, one electron. The electron configuration for Na positive will be just 1s2, 2s2, then to the 6. This is the same as, all right, electron configuration for neon. It's just gonna be Ne. This is the electron configuration for that. Aluminum will lose 3 valence electron. Magnesium group 2 will lose 2 valence electron. Main group element loses their valence electron, and we look in Lewis dot symbol for elements, how to identify the valence electrons. Non-metals gain electron. How do you determine how many electrons are gained? Depending on the group number, let's say 5A, 6A, 7A, and 8A, except for helium. Each element needs to, or you look at how many steps you need to make to 8 to identify how many valence electron will be gained. Nitrogen, for example, 1, 2, 3, it will gain 3. If it is oxygen, it needs 2 to get to 8. If it is fluorine, it needs 1 to get to 8. Therefore, you will see Na3, which means it has gained 3 electrons. Oxygen, it has gained 2 electrons. Fluorine, it has gained 1 electron. So metals tend to lose their valence electrons, non-metal gain the electron in such a way that they end up with 8. So the guiding principle is the octet rule we talked about. Once come to transition metal, most of them, they lose, either 1, 2, or 3 predominantly. They lose their valence electron. Transition metal lose valence electron fast. All right. What does that mean? Let's say iron, for example. Electron configuration for iron is 1s2, 2s2, 2p6, 3s2, that's 12, 3p6, that's 18, 4s1, 4s2, sorry, that's 20, and iron is number 26, so 3d, 3d4. Make sure that we have 26. Iron is number 26, so 20, this is d6, so it's gonna be d6. 6 right there. This is d6. This is electron configuration. So for iron 2 positive, it will lose the highest n value electron. That's what I wanted to point here. The transition metal lose the valence electron, an electron in the highest n value. So this will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 is gone. This is what I wanted to say. The 4s2 is gone, and it's going to be 3d6, 3d6. And then for iron 3, 1s2, d6, 3s2, d6, 3d1. No, 3d5. It just lost to 2 4s2 electron and the 1 3d6 electron, and we are left with 4 iron 3. That's how the transition metals form ions, and then you can write the electron configuration for that. See a learning example here. Based on the octet rule, magnesium most likely to form dash ion. It's just +2. If you don't know how the trend, the pattern in which metals lose or gain electron, you may just end up gaining. But remember, metals tend to lose their valence electron, and +2 means we are less tied to electron, and the correct answer there is A, Mg +2. Mg +2 is the correct answer, because M magnesium, this is group 2A, 2 valence, electrons, 2 valence electron, and this will be Mg2 positive. It will lose 2 electrons. It cannot gain 2. Based on the octet rule, phosphorus most likely form. Again, this will call for locating the position of phosphorus on the periodic table. Phosphorus is on group 5A. So if I have 5A here, there is 6A, there is 7A, there is 8 what? 8A. So 1, 2, 3, we need 3 more. So the charge for non-metals is given by the group number plus, no, not plus, but minus 8, group number minus 8. For example, 5 minus 8 equals to -3. This is the charge. You have that charge on the time. I mean, an ion, which is B in this case. That is B. Correct answer is B. Now, let's move on to section 8.3, the covalent bonding. A covalent bond is a bond formed by or between two non-metals sharing their valence electrons, in such a way that they end up with 8 electrons. That means to fulfill the octet rule. All right, octet rule, sharing of electron between two or more non-metals. The shared electron is represented by a single line, all right? And to determine how many bonds are formed by a non-metal, it stems out from the single unpaired electron, For example, hydrogen has 1 dot. In law is dot symbol for hydrogen. That means gonna form 1 bond when shared. So that oxygen, let's see oxygen 1, 2, 3, 4, 5, 6. Since there are 2 unpaired, oxygen predominantly form 2 bonds. Fluorine, okay, fluorine, which is 1, 2, 3, 4, 5, 6, 7. There is 1 unpaired electron, and that 1 electron will be used in chemical bonding. So we start same number of electrons as the nearest when they form the bond. So here chlorine will be like neon, sharing their valence electron. The sharing here, let's say we have chlorine. This has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. And then we have another one here, Cl, 1, 2, 3, 4, 5, 6, 7. If they form a bond such as this, Cl, the shared electrons here. And these are different color here, Cl, this should be dot. And then I have 1, 2, 3, 4, 5, 6, 7. And then this one is 1, 2, 3, 4, 5, 6, 7. So the 2 electrons being shared here, you see the green dot and the X represent the shared electron, and we use this single line to show the shared electron. And here, this means we have 2 electrons. A single line represents 2 electrons for covalent, so the sharing of electrons so that they end up with 8. We look in details in section 8.5, Lewis structures. The single and paired electron represent, possible number of bonds an element can form. To get an octet rule, the atoms make use of, to achieve the octet rule, the atom make use of unpaired electron when you write the shared electron. Carbon, for example, has 4 dots around it, which is they are available for chemical bonding. Now, we have what we call lone pairs and bonding pairs. Lone pairs and bonding pairs. In the case of chlorine, for example, chlorine gas, let's say for Cl2 gas, we have Cl, and then here, this is where we call bonding. And this one right here, right here, right here, this one, this one, this one. These are lone pairs, okay? We call these lone pairs. I've seen a question on this slide. Once we are done with section 8.5, that draw the Lewis structure for this molecule and state the number of lone pairs, okay? If I look at this chlorine gas, 1, 2, 3, 4, 5, 6, we have 6 lone pairs. So understand that there are 2 types of electron, the bonding pair by looking at the line bonding pair, non-bonding pair. Now there are 3 types of bond you must commit to your memory as far as covalent bonds are concerned. This is a single bond covalent bond, all right? Double bond, triple bond, 3 bonds. Here we have 2 electrons, 2 here and 2 here, which gives us 2 pairs, 1 pair. And then 2 electrons, 2 electrons, and 2 electrons. And then here is 3 pairs of electrons. And formation of the double bond has to do with an atom in the molecule ending up with 8 electrons. When an atom form chemical bonds, especially in molecular compounds, they always, most part unless it is a radical, we'll see the exception in 8.7, the atoms end up with 8 electrons, the octet rule. So to achieve the octet rule, we form either double bond or triple bond. You see clearly in 8.5 when we get to Lewis structure for our compound. Let's see, so you should know the 3 types of bonds: single bond, double bond, and triple bond. How many electron pairs, how many electrons? There are 6 electrons in triple bond, there are 4 electrons in double bond, and 2 electrons in single bond. 8.4, when a chemical bond is formed, it does not mean that always the shared electrons are shared equally between the two atoms involved in the chemical bond. At times, they may be unequal sharing, they may be equal sharing. For complete transfer, of course, it's for ionic. So electron in covalent bond here, electrons in covalent bond are not always shared equally. Why? It's because of what we call electronegativity, all right? The reason why there is unequal sharing is because of electronegativity, which we'll see later in a few minutes. Electronegativity. This is simply ability to attract electrons, or rather to attract shared electron. Let me just say attract shared towards is solved in a covalent bond. The ability of an atom to attract electron toward itself in a covalent bond is what we call electronegativity. And it leads or make the bond polar. It means one portion is partially positive, one portion is partially negative. There is what we call bond polarity, which is just a measure of unequal sharing. Now, this electronegativity leads to unequal sharing. For example, you may see this structure for hydrogen fluoride, but when it comes to sharing, all right, electrons spend more time on fluorine than closer to hydrogen because of the trend on electronegativity. We'll see that later on. Or non-polar covalent bond when there is equal sharing. For example, here hydrogen gas, they will share equally, you know. Chlorine gas, all right, fluorine gas, iodine, I2 or Br2, just to give you, even oxygen O2, there is equal sharing. In a polar covalent, one atom attracts electron toward itself because of electronegativity. We'll see that in a moment, and it is one of the trends you should remember, okay? So the unsharing of, you see, polar covalent, non-polar covalent, non-polar equal sharing for fluorine, equal. So we say non-polar. Fluorine pulls electron harder than hydrogen for hydrofluoric or hydrogen fluoride. This diagram, electrostatic potential map, indicates which portion of the molecule is electron poor, electron rich. Electron poor is always indicated in blue. So the hydrogen will see this partially positive, partially negative, indicating which part is positive or which part is electron rich, electron poor. Do I have to memorize only the three molecules given in this slide? Nope. All you have to know is the trend on electronegativity. Trend on electronegativity. And as you go across the periodic table, the increases. This is periodic table. Electronegativity. So, of course, if there are two atoms, same such as hydrogen gas, all right, there is equal sharing. But now, hydrogen is on this side of the periodic table, fluorine is on this side of the periodic table. Fluorine, based on this trend, based on the trend on the periodic table, fluorine is more electronegative. Therefore, it will tend to pull electron toward itself, making it electron rich. There are some electronegativity values which I don't want you to memorize. All I want you to know is the trend on the periodic table. I define electronegativity. You should be able to define the ability of an atom in a molecule. And remember, molecules are only made up of non-metals. So here, electronegativity increases going across from left on the periodic table to right. And if you look at going down, it decreases. Linus Pauling, he was an American chemist, right? Work on the electronegativity values you see on this diagram. No one will ask you to memorize them, but if need be, you'll be asked to, or you'll be given, and I'll show you where these numbers will be handy in answering a question. And I will give you, or you may be given for a particular element. So note the trend here. You may see this in the exam, next exam or quiz, that as you move from left to right, what happens as you go down, so that given a list of elements, you should be able to rank them according to increase in electronegativity, decrease in electronegativity, or you may identify the most electronegative, the least electronegative element in a question. For example, here, which one of the following element has the lowest electronegative? You have to eyeball and look at on the periodic table. No one will expect you to memorize, all right, the electronegativity values, all right? No one will expect you to memorize these numbers in order to answer questions such as this. But based on the position, this one is number one, all right? So number two, this is number one, most electronegative. The least electronegative is cadmium. This is calcium, this is nitrogen, this is silicon. You should know your elements. Calcium, cadmium, and choice D is the correct. Choice D is in David. This is the correct answer for this question. And still has to do with knowing the trend on the periodic table. Trend on the periodic table. Now, electronegativity and polar bonds. When we say polar covalent bond, that means a covalent bond where electron density is high in one portion of the bond, right? It does not mean that when you have a covalent bond, electrons are shared equal. Polar covalent bond means electrons are concentrated in one end of the bond, where the other end is electron. But there are electrons there, but it's just electron per region. When two atoms share electron equally, are polar and equally. When atoms share electrons and equally, a polar covalent bond resolve. For example, hydrogen fluoride here, fluorine, from what we know now, fluorine is more electronegative. It will pull electron toward itself, where the positive, delta positive, means electron per region of the molecule. Delta negative means electron rich portion of the molecule. There is no complete transfer, by the way. Don't think that electron will move all the way. It's not 100% transfer. Otherwise, it will lead into ionic bond, which we just look in section 8.1. Which of the following molecules contain the most polar bond? By just looking at the elements in all these, fluorine is the most electronegative, and I can tell you the correct answer there is A, the most polar. CCl, I mean, you have to look at where they are. Tellurium and oxygen T or lurium, okay? I'll use the position on the periodic table to stay. So here the most polar is carbon tetrafluoride, because fluorine is most electronegative element on the periodic table. Now, what I was talking about earlier on in terms of the polar, the electronegativity values, electronegativity differences, which we use, this can be used as a benchmark, delta E, and this means difference in electronegativity values. Which you subtract. We use this to tell whether the bond is polar or non-polar. The more polar the bond is. And here is our the benchmark. 1, change in electronegativity. 0 less than 0.4. This is non-polar covalent. Change in, let's say 2 here, change in 0.5 and less than 1.9. This means it's a polar covalent bond. When you subtract the values we looked earlier on, and electronegativity values between elements. And lastly here, change in electronegativity value greater or equal to 2.0. This means the bond is ionic. The bond is ionic. Look at here, the change in electronegativity. This is non-polar, polar covalent, the most polar. So you're just gonna have to look at the values. A dipole moment, we'll see later on how to calculate that. But first, let's see Given the electronegativity values below, okay, hydrogen has 2.1, carbon 2.5, nitrogen 3.0, and oxygen 3.5. Given the electronegativity, which covalent single bond is polar? I look at that most polar here, and C, oxygen and hydrogen has an electronegativity value of, all right, 1.4, 3.5 minus 2.1. If you find the electronegativity values, the difference between these two, 3.5 and 2.1, gives you 1.4. The rest we have E 0.5, 0.4 for A, B is 0.9, the most polar. I'll just use the electronegativity values will be given for that. Now, dipole moment now indicates or is just a measure it's measured in dpi, which is basically the displacement of electron, the measure of a displacement of electrons produced by two equal but opposite charges separated by, it's measured in dipole moment. D, this stands for D, all right, designated using, this is dipole moment. You see that how we use for separating the charge. I don't want to, I know you can read this comparing the ionic bond and covalent bond. Comparing ionic bond and covalent bond, you can read this, make your own notes on the difference between or comparing the ionic bond versus covalent bond, knowing the properties. All right, just have to look on your own. Lastly, before we look at the 8.5 section, we move on to 8.5, drawing the Lewis structure for molecules. Identify the compound with ionic bond, right? Looking at the chemical formula for compounds, you should be able to classify or tell which compound has ionic bond. The correct answer is in this case, please. The correct answer in this case, check, use the periodic table, left side on the periodic table, if it's a metal and a non-metal, you know it has ionic bond. This has metallic bond, this has covalent to non-metals, and we don't have just single atom for that. That marks the end of part A or part B for chapter 8. We'll come back again for part P. This was just part A. Please take your own notes and use MyLab and mastering practice with end of chapter problems. See you. Thank you.